what exactly is caching? To simplify it in one sentence, caching is a mechanism using which we decrease the amount of time and effort it takes to perform some amount of work. That is the one line explanation of what exactly is caching. And a more technical definition of that would be caching is basically keeping a subset of some data. Let's say we have a primary data, and when we keep a subset, not the whole data, a subset of that data depending on the uses of the data, the frequency of the uses and the probability of the next user's time, etc., depending on a lot of parameters, when we keep a subset of some data in a location which is faster to access, which takes less time, and also it is easier, which means it also takes less effort. So technically speaking, caching is a mechanism using which we can decrease the amount of time and the effort it takes to retrieve or to do some kind of operation. That is the technical definition of what we mean when we say caching. And this single mechanism or this single technique is a huge factor in a lot of high performance applications. So let's go through a couple of examples and understand where exactly people use caching and how does it exactly impact the performance of the application and how important it is. And to give you a hint, it is very important, at least when it comes to high performance applications which track latency in 2-digit microseconds or milliseconds. Okay, let's take the example of Google. Pretty much all of us use or have used Google search in our browsers. And what exactly happens when you search some query in Google? Let's say you type something in Google in the search bar and you hit enter. And that query is processed by Google's search engine. They have a pretty complex algorithm and workflow which every query goes through. That typically involves crawling, indexing, and ranking billions and billions of web pages. And that whole process is pretty expensive. And when we say expensive, computationally expensive, right? It takes a lot of computing power, a lot of CPU, a lot of memory resources, and etc. Right? And let's say a query like, what is the weather today? And queries like these are searched millions and millions of times every day. And without caching, without implementing this mechanism called caching, Google servers, they would need to recompute all the results for every single query, involving the current weather of that location, and which will lead to a very high latency and of course a very high server load. Every single query would require going through all the index, running all the ranking algorithms and fetching the results, which would in turn significantly slow down the response times. Now, when we insert caching in this, so what Google does, the search engine, is it uses a distributed in-memory caching system to store. We'll see what is in-memory caching system soon, but that's how Google does. It uses a distributed in-memory caching system. Distributed in the sense, the servers of the caching system are spread across the whole world. They are not just concentrated in a single location, but they are spread across all over the world. And those cache servers, they store the results, whatever results are returned by all those ranking algorithms and all those different algorithms that are involved in the whole Google search workflow. They get cached or they get stored in these servers. And when a user searches, the system first checks whether the results of that particular query, let's say you search the weather in some city of India. So the system checks whether the results of that is present in the cache or not. If the query is cached, that means it is a cache hit, right? That's what we call. It's a technical term. Whenever we find the data that we are looking for the cache, we call it a cache hit. If the system finds it, it returns the results instantly, right? Retrieving data from a cache is very fast. That's one of the reasons we use cache in the first place, right? And we'll see why exactly fetching data from cache is fast as compared to our traditional databases like disk-based databases, right? Which you saw in the previous video. Okay, we'll soon get into that. Well, for now, we are just going through some examples to understand the gravity or the understand the importance of caching in different platforms. And let's say the system does not find the result, right? The query that the user typed that has not been typed before. So the system, the cache, it does not have the data. So what it does, it goes through the normal workflow, all the ranking, all the sorting, whatever algorithms are involved, and then it takes that result and it caches it so that the next time the same user or some other user tries to type the same query, then those results can be fetched from the cache and can be returned to the user. Okay, that's one example. Taking another example, say another popular platform, and we take Netflix. How exactly does Netflix, a huge and a global streaming platform, which delivers different kinds of content like movies, series, and animes, etc., how does it deliver the content to millions of users all over the world? And its teams large, and when we say large, it can be multiple terabytes, because the way these streaming platforms work is, for a single video, let's say for a single movie, it stores different resolutions. Let's say we have a movie called movie 1, then it goes through a process called encoding, and it prepares different resolutions for different devices and different network speeds. So for a high level explanation, let's say it has a 1080p resolution, another for 720p, another for 480p, etc., right? And depending on your network speed and depending on which device you're trying to access the content of Netflix, it dynamically sends an optimized version of that content for or that movie, right? So that you don't waste your bandwidth and the load gets decreased on the Netflix server also. Okay, that's all about the encoding part. But talking about how does it exactly sends or delivers hundreds and thousands of terabytes of data to millions of users spread across all over the world, right? Since Netflix is a global streaming platform, and that too with minimal amount of buffering and decreasing server load, so that Netflix server don't crash. And the way it does is it uses something called CDNs, and CDN also known as content delivery network. The way they work is Netflix has its own servers, its own originating servers. Let's say it's somewhere in the US, right? In US, there are different data centers and different locations where it has its own servers, right? And its own server racks, which store the actual movies, right? Here we have the actual movies, but what it does, it goes an extra mile, and what it does, we have our world here. Let's imagine this is our whole world. So at different locations all over the world, and those locations are of course chosen by the infrastructure that is available and how much network connectivity, etc., and a lot of parameters. So all over the world there are different locations, and these are called edge locations. Edge, right? These are called edge locations because these servers are strategically placed so that the latency of the user's connection in that region, let's say there is a server in this part of the world, then for this region, the latency of data or whatever requests are served from the server is going to be minimal, right? Let's say we have US somewhere here, minimal, as compared to all the requests going through the originating server, which is situated in US. And that part of the data center serving requests from all over the world, then that will be a situation where all the people who are in US, they will have low buffering time because geographically speaking, they are closer to the servers that are serving the content. So of course, their latency is going to be very less as compared to people from the other side of the world, right? Let's say from India. And that is the reason this is a strategy that a lot of companies use, right? Not just Netflix. CDNs or content delivery networks are very common, and a lot of companies and a lot of small and big companies use them to efficiently deliver different content. It can be video files, it can be images, it can be also web pages, right? Web pages which consist of static assets like JavaScript, HTML, or CSS, etc., etc. Those kinds of assets are also served from different CDNs. When you use a platform like Vercel, they also have an edge network like this, and their servers are also spread across all of the world. So when you make a request to a server, to a front-end app which is deployed in Vercel, so depending on your location, that request is served from the closest regional server to you instead of going to the originating server, right? So CDNs are very common, and this is how Netflix, the global streaming platform, serves billions and billions of users with hundreds and thousands of terabytes of data every single minute using this concept called caching the content at edge locations, right? We again come to this concept called caching. If you remember, the definition of is called taking a subset of a primary storage and placing it in a way that accessing data from this source is much faster than accessing data from the primary storage. So taking the example of Netflix, Netflix takes some data, a subset of the data. Of course, it does not cache all the data of the Netflix storage in all the edge locations. That would incur a lot of cost and of course a lot of resources also. They use a lot of algorithms, machine learning algorithms, depending on what type of content people of that region are watching, right? They do a lot of trend analysis and a lot of real-time data, etc., right? A lot of computation goes behind deciding what data, what subset of the data to cache, so that the amount of time and the effort can be decreased to access that data, right? You cannot just put everything in cache, right? That defeats the whole purpose. And caching is also more expensive than storing the data in secondary storage or disk-based storage. And that is the reason we don't put everything in cache memory, right? Disk storages are relatively cheaper and also offer a lot of capacity. Now, moving on to a third example. Let's take a platform called X, or also previously known as Twitter. Okay. And for this, you can take any social media examples. So this example can be applicable to Facebook also, and you can say LinkedIn or YouTube videos, etc., right? The same, all these social media platforms implement the same kind of strategy for, let's say, if you're familiar with how Twitter, the platform works, Twitter has a section called trending topics, right? And what Twitter does, or what X does, is it identifies trending topics by analyzing millions and millions of tweets in real time. It analyzes all the tweets that people are making all over the world, and it extracts some kind of patterns and some kind of trends, and it calculates. And that calculation is very expensive. It takes a lot of machine learning based algorithms. It takes a lot of GPUs and a lot of infrastructure, right? And it also involves processing a large amount of data, terabytes and terabytes of data, because we are talking about analyzing tweets of people, millions and billions of people all over the world. So that is the reason, to avoid doing this computation of this large amount of data and to use this much amount of resources, to avoid doing that again and again, because every time, let's imagine if Twitter did all this calculation every time some user went to the trending section of the then of course the server will crash in minutes or seconds, because there are like billions of people, and if even half of them are trying to access the trending section and every user triggers this calculation, this expensive calculation, of course the server cannot handle that and they will crash. So what Twitter does, of course, to avoid doing this computation, this heavy computation for each request, it caches it. Okay. And by now you can see the pattern, right? Every time there is a situation where it's either about doing a lot of heavy computation or heavy amount of data. When we have situations like these, when we want to avoid doing a lot of computation again and again, and when we want to avoid sending large amounts of data to a lot of users, these are the two scenarios, the common two scenarios when caching comes into play, right? So coming back to the Twitter example, Twitter caches all these trending topics, because for a trend to change, in a particular region, right? Let's say you are in some country and that country has ongoing elections. So elections being the trending topic in Twitter is not something which is subject to change in, let's say, seconds or minutes, right? At least it will stay in trending section for a couple of hours or a couple of days. And that is the reason, since it is not dynamically changed, it is not subject to minutes and hours of change. That is the reason it is very safe to cache the trending section of Twitter. So what Twitter does, it takes all this data, all this millions and billions of tweets, and every few minutes. So we are, of course, we cannot know what is the exact algorithm or what is the exact duration that Twitter does all this computation, or what computations exactly Twitter does. But taking a rough estimation for the sake of this example, every few minutes, Twitter takes all this data from different regions and it executes different algorithms. Okay, on a very high level speaking, different machine learning algorithms and trend detection algorithms, and well, a lot of those complicated stuff, and it stores them in a in-memory cache, something like Redis. We'll see what are some famous and popular in-memory cache technologies, but Redis is one of them and it is very famous. So let's imagine Twitter calculates all these trending topics and it stores it in an in-memory key value store based database like Redis. And when the users request it, then it takes that data from the cache. Instead of computing all of that again, it takes that data from the cache and sends the user. And that is the reason the moment you open your phone, you get that data instantly. You do not see any kind of delay, right? You do not see any kind of significant loading time. Of course, if you have a very bad internet connection, you'll see loaders and all. But if you have a generally fast internet connection, it's pretty fast, the whole UI interaction. And with those three examples, we kind of have a pattern here that every time we want to avoid doing some kind of heavy computation or some kind of heavy data, when we want to avoid these two kinds of situations, we resort to what we call as caching. And now that we know caching is an important concept and it is implemented everywhere, so on a high level, and since we want to limit the context to especially backend engineering, something, all the concepts that you as a backend engineer are going to deal with on your day-to-day life or on your day-to-day development. Because of that, we want to limit the context of caching, because if we go around and start to find the implementation of caching in different contexts, starting from hardware to software to browsers, etc., it's going to take a lot of time. And of course, it is very good to have that knowledge, but it is very difficult to cover all of that in a single video. Right? So we'll keep it relevant. On a high level, when we talk about caching, you will see three levels of caching. At least you'll notice these three caching more frequently as compared to other kinds of caching as a backend engineer. Those three are: first is network level, second hardware, and third is software based. It's not purely software based. Of course, software based caching also uses hardware based caching to provide the performance, but it's called software based caching because of the interaction and because of the means of interaction. You'll be dealing with some kind of library, some kind of software to interact with this cache. That's why it's called software based caching, but it's of course not purely software based caching. It works with the hardware based caching. Okay, now going into each of that, let's start with network cache. So inside network cache also, there are different use cases, a lot of use cases of caching, but the two major ones that you'll see frequently are, the first one is CDNs, as I just explained in the Netflix example, how Netflix serves and delivers all these heavy terabytes and terabytes of content to users all over the world. There we discuss CDNs briefly. So here we'll go a little more deep into CDNs. And the second thing is DNS. DNS is also something we use a lot every day. We don't really notice the use, but it is happening, right? And caching is also a very important part when it comes to DNS querying. So let's explore these two things which fall under network level caches. So first one is CDN, also known as content delivery network. The whole idea of CDNs or content delivery networks are to cache content on servers that are geographically, as I said, geographically closer to the end users. That's why they are also called edge nodes or edge servers or edge computing. Any kind of edge word that you notice, that basically means it is happening in a server that is closest to you, instead of a single server or single servers in a particular region or the originating server, right? So CDNs make use of this concept that the content will be stored, they will be cached and served from the servers that are closest to the users to minimize the amount of latency and minimize the amount of computation or the amount of resources of the originating server. So on a high level, this is how CDNs work. So let's imagine a user makes a request and it requests for some kind of resource, a resource like an image or a video or a web page, right? Some kind of resource by entering a URL in their browser. Okay, that's how we typically access some kind of data over the internet, right? Through the URL of our browser. And that browser sends a DNS query to resolve the domain name, whatever the domain name that we have typed of that image, of that video, or that web page. The browser sends a DNS query to resolve that domain name into an IP address, because that's the use case of DNS, right? DNS names take domain names and convert them into IP addresses so that our browsers can access the actual location of the server, right? Now, next what happens? The CDN's domain name system, the CDN's DNS system routes that particular request to the nearest POP. POP is also called as point of presence, and it is just a fancy term. It just basically means a particular region where there are multiple edge servers. These servers that we are seeing here, there are multiple edge servers in a particular region, and that concentrated region is called POP or point of presence for that region, right? POP is just a collection of multiple edge servers for a particular region. Now what happens? The CDN's DNS system, it routes the request to the nearest POP, right? The nearest region which has multiple edge servers so that it can serve the content, right? So that is the responsibility of the DNS system, because that's why DNS is a very important component when it comes to CDNs, and it routes the request depending on multiple parameters like user's geographic location, right? And the network conditions, whether the user has a stable internet connection or it has a bad internet connection. If it has a bad internet connection, depending on that, it might route to a different POP or different edge server. So because this edge server may only have the content of the highest quality. Let's say you have a bad internet connection and this particular POP or point of presence, this only has 1080 pixel formats of the video, right? This is just a rough example. So depending on your network condition, the DNS system, the CDN's DNS system, it will check that since you have a bad internet connection, it will route it to a POP which has videos of lesser qualities so that you can load that resource with minimum amount of buffering. Okay. For example, if a user in New York requests a particular resource, an image or video or web page, the CDN system will direct the request to your POP near New York, right? That's how the requests are routed to the nearest POP using DNS. Next, what happens? The edge server, once it reaches the POP, which basically means a collection of edge servers. Now here what happens, it checks if the requested content, that particular video, that particular web page or image or whatever that is, whether it is in the cache or not, if it is already cached or not. Depending on that, it is either a cache hit or a cache miss. So as I already said, if whatever we are looking for, if it's already in the cache, then we call it a cache hit. If it's not, then it's called a cache miss. If it is a cache hit, it finds the resource and it just sends the request to the user, right? It is the happy path. But if it is a cache miss, what happens? The content is not in the cache. So the edge server, whatever edge server that is handling this particular request, it fetches it from the originating server. Let's say the originating servers are somewhere in US, right? And the user is in India. So it is the responsibility of that edge server to fetch it from the US servers, the originating server where the actual resource is present. Of course, the cache also has the copy of the resource. It is not a fake resource, but all the resources. Basically, we are talking about originating servers have all the resources, so that CDNs can fetch from them and serve users the content. And that's how typically a CDN, a content delivery network, works, using DNS and point of presence and originating servers and all these buzzwords. CDNs also use a concept called TTL, time to live, right? So depending on that, they decide how long to keep a particular piece of content. So usually companies decide some kind of fair duration, right? This content should only be cached for the next few hours, because after that it might have a new version, or there might be regional changes, etc., right? So it is a safe default, so that after this amount of time, if a new request comes, then instead of serving the old content, it fetches from the originating server, takes the fresh content and serves it with a new TTL, time to live. Right? So a typical CDN workflow works, and it is considered as a network level cache. The second use case of caching when it comes to network layer is DNS queries. They also make heavy uses of caching to minimize the latency of all the DNS queries that are happening from billions and billions of users at the same time. So let's imagine another user scenario so that it's easier to keep track of how DNS actually works and where exactly does it actually implement the caching workflow. So let's imagine a user enters something in the URL, let's say a domain name example.com, right, in their browser, and they press enter. What happens? The first thing, we are just only focusing on the DNS part. Of course, when you type something in your URL bar, a lot of things happen, but we'll be focusing on just the DNS part. Right? So the users divides. So after you hit enter, the user's device, whatever the device it is, the laptop or the smartphone, it sends a DNS query, and it sends it to a recursive resolver. It's a technical term. We'll see what it means. It sends the DNS query to a recursive resolver. And this resolver is typically provided by the user's ISP. ISP basically means whatever company it is you are taking your internet connection from. So if you're from India, it could be Jio, it could be ACT, or it could be Airtel, right? So that is your ISP. Now this resolver, this recursive resolver, this is provided by your ISP, your internet service provided. Or it could also be provided by some third-party DNS providers. Like Google has a public DNS provider, or Cloudflare also has a public DNS provider, etc., right? So it can be either of that. It can be your ISP, or it can be a public DNS provider like Google or Cloudflare. Now, second thing, what happens? The DNS query is routed to your recursive resolver, which can be in your ISP or a public DNS server like Google or Cloudflare. It does not matter. We'll see what exactly happens once the query reaches the recursive resolver. The recursive resolver, it does the following steps. First thing what it does, it first checks the local cache to see if it already has that particular IP, right? Some random IP. It checks, once it has the query, it checks whether it already has that particular IP cached in its local system. When you say local, it means without accessing a remote storage or anything like that. In its local primary storage or secondary storage, or disk-based storage, or whatever, right? In its own system. It checks whether it has the entry for this IP in its local cache or not. Depending on that, either it is a cache hit or a cache miss. If it is a cache hit, the resolver immediately returns the result. And what is the result in this case? The DNS query was to check what is the IP of example.com. So it checks whether example.com is in its local cache or not. If it does, then finds the corresponding IP address and it returns it to the user, to our browser or to our smartphone or whatever it is, right? But if it is a miss, if it did not find it in its local cache, it sends that query to other resolvers. What are these other resolvers? We proceed to the third step here, right? If it does not have the result if it does not have the corresponding IP address for that particular domain, example.com. It misses it here. It is a cache miss, and it queries other resolvers, and it is called querying the root server. Okay, there are a lot of root servers, I think 13 or 14, I don't know the exact figure, but these are called root servers. Okay, there are multiple root servers spread all over the world, and they don't necessarily have the particular IP. They don't have the result for what is the IP address of example.com. But what they do have is they have the address of the top level domains, right? Top level domains like .com, .co, .in, etc., etc. They have the addresses or referrals for these top level domains or these top level domain servers. Okay, we are talking about other servers now. Now, since it is example.com, it sends the address or the reference of the .com top level server. Next, you proceed. It reaches the top level server for .com. Okay, the TLD for the .com top level domain, right? And from there, that also does not have the IP address of example.com, of course. Then this sends the address for the authoritative name server for example.com. It has the address for the authoritative name server for example.com, and it sends the address of that. Then what happens? The recursive resolver, right? We are still talking about the recursive resolver, which has the responsibility of finding the IP address of this particular domain name. And it is called recursive because it goes deep and deep and deep into different servers until it finds the IP address. That's why it's called a recursive resolver. Okay. And at last, we reach the actual authoritative name server for example.com. And from there, we can take the IP address, whatever IP address it is, can take that and it returns it. Where exactly caching comes into play here? DNS heavily depends on caching because of how much of work it is to recursively reach out to different servers and finally get the IP. That's the reason DNS heavily depends on caches, so that it does not have to do all this work for every single request. So that it has some kind of local cache which it can use for further requests. It only wants to do it once for a certain amount of time, right? So most operating systems, it can be Windows or Mac or Linux, maintain some kind of local cache for DNS. Okay? And when a user requests a particular domain, the OS, the operating system, checks its local cache first. Okay, before it goes to your ISP, the recursive resolver, etc., it checks its local cache. If it can find it, then it skips going to the query resolver, the recursive resolver, and immediately finds the IP address and goes to that and whatever the normal browser flow is. Then the next level, if it does not find the entry for that particular domain, then the next level of cache is browsers, of course. Browsers, most of the modern web browsers like Chrome, Firefox, they maintain their own DNS cache. Okay. After our operating system, the next hierarchy, the next level of caching is implemented by our browsers. They have their own local cache for DNS, so that if our operating system cannot provide the corresponding IP address, browsers also try to maintain their own cache. They check if they have the IP address of a particular domain from some previous request. If it does, then they can skip going to the recursive query resolver and they can immediately access the website. That's the next level. The next level of cache is from the resolver, the recursive resolver that we talked about, which recursively tries to find the IP address until it finds it in some server, whether it is the root server, the authoritative name server, or whatever, right? That recursive resolver, which is either provided by ISP or something like Google public DNS or Cloudflare, right? These components, which are known as recursive resolvers, they also maintain their own cache, so that if for some request they can find the corresponding entry, they can immediately return it, so that they can skip going to all these different servers to find the IP address, right? And beyond that also, when we talked about authoritative name servers, they also have some kind of cache Not all of them implement it, but some of them do, and using which they can also skip making further requests to further servers, right? So as you can see, DNS also implements caching heavily in multiple layers. Next we have is the hardware level caching. So if you're from a computer science background, you'd be already familiar with all these concepts. What is L1 cache, what is L2 cache, L3 cache, what is main memory, what is hard disk, etc., etc. So caching is also implemented at hardware level to make computations faster and to make a lot of CPU level operations faster. So on a high level, without going into too much technical side of it, you can see that we have here our CPU chips, which do the actual processing. Then we have multiple layers of caches. We have the L1 cache here and the L2 cache, and we also have the L3 cache, which is a memory unit which is shared between different caches, right? This memory is shared between different CPU units. Then we have the RAM or random access memory, which is also called as the main memory. And then we have the secondary storage, hard disk and network cards, etc., etc. So what exactly happens? CPU keeps these memory units, also called as L1 cache, L2 cache, and L3 cache, so that it can cache some of the repeated computations or some data which are frequently used or which are going to be used. Say, to give an example, if you are familiar with the concepts of arrays, the reason arrays are a very good data structures for sequential access is whenever you start traversing the elements of the array from a particular direction. Let's say you have 1, 2, 3, 4, 5 here. The moment you start traversing here, CPUs or different computing units inside your processing units, what they do through different predictive algorithms, they take the entire memory unit and they put it in some cache, right? It can be L1 cache, L2 cache, depending on the predictive algorithm. And that's the reason accessing elements sequentially in an array is a very fast operation because of predictive algorithms of the processing unit. That is just one example of how hardware level cache works. The thing that we want to focus here is this part, the random access memory or the main memory, it's considered. And whenever we talk about major caching technologies, say Redis or memcached, these are called in-memory key value store based databases. And they are called in-memory databases because they store data in your main memory or the random access memory. And it is called random access memory because compared to hard disks or SSDs, in which you can access the data in a mechanical way. So if we take hard disks, for example, there is some kind of head which revolves around the disk and it finally finds the data, right? It is a mechanical operation. And compared to that, main memory or random access memory, it has a bunch of capacitors and all, and through the use of electrical signals and with the direct access of different parts of the memory addresses through their addresses, it can directly access the data with a single electrical signal. And that is the reason it is called random access memory, which means it does not matter from what direction you try to access the data, the speed and the time is going to be the almost constant. That's why it's called a random access memory, and it is very fast to access data from this part of the memory. But the problem is we don't have random access memory or the main memory in abundance, even though we have speed at our disposal when it comes to random access memory. They have limited capacity and also they are volatile in nature, which means whenever you turn off your power, whatever data is stored in random access memory, it goes away, right? It clears, it starts fresh whenever you start your computer. Right? Because of their volatile nature and because of the way they are created, at least from the hardware level, they are created with the trade-offs that we are trading off non-volatility and capacity for speed, right? So that's the reason we cannot completely replace a hard disk or our traditional disk-based storage with random access memory, right? They have their use. They are fast when it comes to data access and data retrieval, but they are not a replacement for our secondary storage. Okay. Storing data in secondary storage is permanent in the sense they are not volatile. Does not matter whether your program is accessing it or not, whether your computer is on or not, the data persists there because it is physically writing the data in the disk. Right? That is the reason hard disk or secondary storage have their use and primary storages have their own use. Primary storage have very fast data access time, and secondary storages have slower data access, but they provide the safety of persistence. And that is the reason technologies like Redis or memcached, these databases, they make use of this random access memory or the main memory to store their data. And behind the scenes, for persistence, they make use of the secondary storage. So with some kind of mechanism, when the program starts up, they take the data from the secondary storage and load it in the main memory again, so that you have your data persistence. But when you retrieve it from the primary memory. Right? It's the responsibilities of these programs, Redis, memcached, or whatever caching technology, the in-memory caching technology that you are using, is their responsibility to implement persistence, etc., with the secondary storage. But when we are talking about accessing the data, whether retrieving it or modifying it, it happens with the primary memory. Right? That's the reason data access operations from these databases are very fast. And finally, coming back to the context of backend development, technologies like Redis or memcached, or if we are talking about cloud technologies, then technologies like AWS Elastic Cache, these come into play. They provide some kind of storage, and that storage is based on the primary memory. And that's the reason data access operations are very fast. We call these technologies in-memory key value based NoSQL databases. Right? There are 4 components here. The first thing we already saw, they are called in-memory based databases because they, as compared to traditional databases like Postgres or MySQL, they are not stored in disks, right? Secondary storages. They are stored in RAM or primary storage. That's the reason they are very fast, right? That's why they are called in-memory databases. The second thing is key value based, as compared to traditional databases, relational databases, which have very strict schema, and you have to create tables and you have to create rows, etc., right? Instead of that, here the data structures are pretty simple. You have keys and you have values. You have a particular key, and for that key you can store anything. It can be a list, it can be a JSON, it can be a string, number, etc., right? Different technologies offer different data types, so you won't go deep into that. You can do your own research for that. And that's the reason they are called key value based NoSQL databases, right? They don't enforce the strictness of traditional SQL databases. And that's about the name. Now, since we are talking about databases like this, which we use in our day-to-day backend development, there are 2 types of caching strategies. The first one is lazy caching, or also known as cache aside. And the second one is known as write through. And surprisingly, we have already talked about this, so we won't go very deep into this. All in all, lazy caching basically means, let's say there is a client and it is requesting some resource. So that server checks whether that resource is present in the cache or not. If it is, then it returns that resource. If it is not, it fetches it from a different storage, right? Some kind of primary storage, and it fetches it, it gets the data, it stores it in the cache, and then it returns the result to the client, so that the next time the client makes that request or some other client makes that request, it again checks and it finds that in the cache and it returns it. That's why they are called lazy caching. You don't proactively cache things by predicting from client interaction or patterns, etc. You just cache it when someone actually requests it. That's why they are called lazy caching. And it is a pattern that is very famous in a lot of different contexts in backend development. The second one is called write through caching. It is more about the cache updation strategy, which basically means every time something changes, right? Every time there is a post call or put call or patch call where you are actually changing some resource or creating some resource in the database in your primary storage, what you do, you make the change for that resource in your database. You make the data query at the same time, in the same API call, in the same execution flow. you also make the same change in your cache so that the next time the request comes, you can serve it from the cache. And which also means all your operations, all your write operations bring more overhead, because at the same time you have to update the database and the cache at the same time. But the advantage here is your cache is always fresh, right? It is never expired. You never serve old data. Since you update the data in the database and the cache at the same time, your cache is always fresh. So those are two major strategies that you will see frequently in your day-to-day development. The next major component when we are talking about technologies like Redis or Memcached is the eviction policy. Something else that we should be aware of is the eviction policy. And what it means is, when you have a cache, as we already know that in-memory caches like Redis, they use primary storage or the random access memory, which is limited in capacity as compared to the secondary storage. So it is pretty obvious that at one point we'll run out of memory, or if we are using a managed storage like AWS Elastic Cache, right? So they have a storage limit, right? In these conditions, we are bound to run out of memory at some point. And at that point, we have to decide that we want to delete data from our cache, right? Of course, from the initial part of the video, we have already discussed that cache is only a subset of the data which is frequently accessed, which we store in a different location so that the retrieval is fast, right? So the keyword to focus here is a subset of the primary storage, right? We cannot store all of the primary storage to cache. And that is the reason we have to decide that at some point we have to let go of some data so that the new data can be stored. New data which are more important, which have higher priority than whatever the old data is. And that's why we have the eviction policies. Eviction policies basically means you decide how are you getting rid of the old data so that new data can be stored in the cache. So a couple of strategies are, the first one is no eviction. And this basically means you do not configure any eviction policy. The next time you try to insert data into the cache, you get some error that the memory is full, right? Does not make any sense. But if you have not configured any eviction policies, then the configuration is called no eviction. The second one is LRU, also known as least recently used. This algorithm basically checks that which pieces of data are least recently used. Basically means if there are other data points, let's say we have 4 keys in the cache, and now the memory is full, right? And the database, something like Redis, they keep track of when was the last time a particular key was accessed. Let's say this key was accessed today, and this was also accessed today, this was also accessed today, but this was accessed yesterday. Now when a new data point comes across, let's say we want to store key 5. When 5 comes across and this cache is full, this has to make space for 5. And in this situation, if we have configured least recently used eviction policy, what it does, it checks which is the data point, which is the oldest accessed data point. And since 4 was accessed yesterday and all the other ones were accessed today only, it selects this, that you will go out and 5 will go in. This is what we mean when we say least recently used or LRU cache eviction policies. Third, we also have LFU, which means least frequently used. So going back to the earlier example, forget about the time. Let's say, okay, so we have 4 keys, 1, 2, 3, 4, and 5 comes across. Now, instead of tracking when was the last time this key was accessed, it also tracks what is the frequency of the access. Let's say 1 was accessed 5 times, and we are talking about so far, right? The key number 1 was accessed 5 times so far, and 2 has been accessed 10 times. Then we have 3, 6, and 4 was accessed, let's say 23 times, right? Some random numbers. Now, when 5 comes across, it checks which is the data point is least frequently used, which means the access frequency is the least. So if we check this, the key 1 was accessed the least number of times, right? The 5. The other keys are being accessed more frequently, and that is the reason it selects 1 and says that you will go out and 5 will go in. That's what we mean when we say least frequently used cache eviction policy. Then we also have TTL, time to live based eviction policy, which basically means in Redis we can configure what is the TTL, time to live, for different keys, right? So depending on that, a particular key can be invalidated automatically depending on the TTL, time to live. Okay, and that can also be part of the eviction policy. So in the same scenario, when 5 comes in, it checks that which of these keys have the lowest amount of TTL. So which key is going to be expired soon, right? Depending on that, it selects that key and takes it out and inserts a new key. And that's what we mean when we say time to live, TTL based eviction policy. And that's pretty much all you need to know when it comes to the technicality of in-memory caches like Redis and all. Rest of it is pretty straightforward. You take whatever compatible library is available in your corresponding programming language. Let's say Node.js has Node Redis or something. So depending on that, you just use the library. It's not very complex. You provide a key, you provide a value, you store it, and when you want to retrieve it, you provide the key and you get the value, right? It is pretty straightforward. It has no complexities like SQL queries and aggregation, etc. It's pretty simple to access, right? But all this technical familiarity with how the technology works behind the scenes, what are the major components, it helps you make sense of the whole thing and make better decisions, etc. So now that we have discussed all the technicalities of in-memory databases like Redis, Memcached, let's see some examples. What are some use cases? Where do we actually use technologies like Redis, the in-memory databases, and a typical backend engineering workflow? And one of the major use cases is database DB query. So let's take an example that you have an SQL query which has a lot of joins and it tries to join a lot of tables. It does a lot of aggregation, right? And finally, it ends up with a few rows. Okay? It is a very compute intensive operation because you have a large data set, let's say millions and millions of rows, and it is a very compute intensive data set. And you have, through monitoring, you have noticed that this particular API, which calls this particular database query, it is hit pretty frequently, right? It is, let's say, in your landing page or in your dashboard page, and a lot of users are hitting this API and it is putting a lot of load in your database. So what you can do, you can take that particular query. In the next line, what you can do, you can cache the result with some TTL, time to live. You can say that for the next 1 hour, cache this result, and when the next request comes, check if the result is present in the cache, then serve it from there. Otherwise, do the calculation once and store it in the cache. And whenever some other modification happens, you can manually change the cache, or you can delete it, or you can handle it accordingly, right? Then whenever users hit that particular API, instead of putting the load on the DB, you can directly serve that particular result of the query from a cache, right? That is a good example, right? Whenever you have a very compute intensive database operation and it is being called pretty frequently, then you can cache that result to save some computing time, save some resource, and to reduce the latency of the API call. Also, to take some real world examples, e-commerce websites like Amazon, they also cache product details, prices, and inventory data, etc. to avoid querying the database for every single request. So imagine there is some sale going on for a MacBook and all, and if Amazon did not cache the details of a MacBook for that particular product, then during the period of the sale, millions of users hit that particular web page, and the fetching the image of the MacBook or fetching all the product description of the MacBook, these are all database operations, right? And the database will get a million requests, and that puts significant load on the database, and for no reason, because information like product details for a MacBook, it does not change very often, right? So it is a very good candidate for caching. So that's the reason websites like Amazon, platforms like Amazon, they cache static data like product details, prices in some cases, so that they can reduce the load on the database, and the database can actually do the important stuff instead of serving the static content like product details. The same way, social media platforms, let's say like Twitter or Facebook, they cache user profile data, user profile data is not something that changes very often, right? Maybe a couple of times in a year, right? That's the reason they cache the user profile data so that every time that data is fetched, that is served from the cache instead of from the database. So imagine if it is a social media profile of some celebrity. In that case, that particular page and that particular API of fetching the user profile details of that celebrity, that might get hit, let's say, 1,000 times per day, right? Or if they have an upcoming movie, maybe 1,000,000 times a day. In that case, putting all that load on the database does not make much of a sense, since that user profile information is pretty static most of the times. It can serve that content from cache, right? And even if the user makes some change, they can invalidate the cache and put the new entry. But it is a pretty read heavy operation, as you can see from the pattern. And whenever we have a read heavy operation and the write is pretty infrequent, we can make use of caching. Okay, so database caching, database query caching is one of the primary examples of when we use technologies like Redis or in-memory databases. The second one is session, storing session. So if you have watched the authentication video in this playlist, you might be aware of this. In a typical authentication flow, after a successful authentication, a session token is generated for that particular user, and that session token is stored in some kind of storage, right? And ideally, it is stored in Redis or a in-memory database, so that every time the user makes a request or an API call, we have to fetch that session information from somewhere, right? If we did not use Redis, we'll have to fetch that from our database. And as you already know, fetching data from random access memory or primary memory, or in this case, cache like Redis, is much faster than fetching data from a database. And that's the reason, in order to avoid latency in every single API and to avoid putting load on our database, people usually store session tokens, authentication related session tokens, in Redis or any in-memory databases, right? That is another use case of Redis. Third is API caching. So let's say in your backend, you are making use of some external API, let's say some weather API, and you are taking the information from that and you are doing some kind of computation to serve your own frontend. Now, every time your frontend makes a request to your API, if you do not make use of caching, you also make another request to the weather API to fetch the weather data. And if you have a lot of users and they are making multiple API calls to here, you also end up making a lot of and thousands of API calls to this external API. And usually, since external API calls have some kind of limit, some kind of rate limit, or some kind of pricing based on how frequently you're calling them, you will quickly increase your billing or you will hit your rate limit. And since in this case, it is not real-time data, right? It is a weather data, which is safe to cache. Weather data does not change in like seconds or minutes. That's why it is a kind of data that is safe to cache. So what you do, you fetch that information from that API, you cache it, and you make use of that in all the subsequent requests that is coming from your frontend. And you can use something like TTL for, let's say, of an hour. So you cache this data for an hour, and for the next 1 hour, all the requests will use the value of the weather data from the cache. And after an hour, the cache automatically invalidates it. And the next time a request comes, instead of taking it from cache, you'll fetch the weather data again, you'll put it in the cache, and then you return the request, right? Whenever it comes to interacting with external API, we think about caching so that we can decrease the billing or we can avoid hitting the rate limit. And one last use case that comes to mind is, since we are talking about rate limiting mechanism is also implemented most of the times using a technology like Redis or any in-memory caches. Because the way rate limiting is implemented is, it is usually some kind of middleware which sits somewhere in the middle. Since it is called a middleware, that's the reason. Before the request is passed to your whatever route or controller or whatever it is, and this is the browser or any client that is making the request, and this is the entry point to your particular server, right? And this is the middleware, the rate limit middleware. And what it does is, it takes the header, some kind of header which gives it the IP address of the user. Usually the header is something like X forwarded for it. This header is mostly used for implementing rate limiting to find out the IP address, the public IP address of your client, wherever the request is coming from. And this is usually added by reverse proxies like Nginx or whatever that you are using. So that is not the point. The point is, the job of this middleware, the rate limit middleware, is it takes this header out from that request. Every request has some default headers associated, which you already know. Then it takes this particular header out from that request and it checks the IP address. And usually rate limits have some kind of default mechanisms of durations, like how many requests. Let's say you can only make 50 requests per second, right? And these are mostly implemented to avoid uses from bots. Let's say if it's a very compute intensive API, then rate limiting can help you save your resource, right? Save your compute. Now, let's say this is the condition. A particular client can only do 50 requests in 1 minute. Let's say 1 minute. Then whenever a request comes, it checks that whatever value it is in the X forwarded for header. Let's say it finds some IP 10, 12 dot some kind of IP. Since we are talking about a key value store, it saves some kind of counter. Say that this is the IP address. For this IP address, for the start of this minute, the first request came, I got one request. The next time the request comes, it checks the cache. So far 1 minute has not passed, right? That's why it checks and it increases the counter. From 1 it makes 2. Same way from 3, 4, every time a request comes, it increases the counter, so that within a minute, if the counter exceeds 50, then what it does, it blocks that request and it sends an error response of 429. And when we send a status code of 429, it means too many requests. This is how a particular workflow looks like for rate limiting. Now, coming into caching, this particular part where it stores the counter is usually in Redis or any in-memory databases, because if it stored it in a relational database, something like Postgres or MySQL, that is possible. Of course, that is possible. It has a persistent storage and we can retrieve data, etc., etc. But difference is, taking data out from a relational database takes more time, right? Even a difference of, let's say, 20 or 30 milliseconds, that makes a difference on what is the latency of the API. If we stored it in a relational database, then for each request, we'll be making a database call. In turn, the first thing is, anyway, the latency will be increased for that particular API, since we are making a database call unnecessarily for each request. Second thing is, the load on our database also increases. Let's say there are like 1,000 users, then 1,000 users are making 100 requests per a minute. Then our database will be flooded with just the requests of rate limiting, right? That is the reason we want to separate this out for 2 reasons. First is, of course, to make it as fast as possible so that we can minimize the latency of APIs, and also to decrease the database load. And that is the reason whenever we are talking about implementing rate limiting, we make use of in-memory databases like Redis instead of storing it in our relational databases. And with that, we have pretty much covered what is caching, why do we use it, some real world examples, and why do we use in-memory caches, why is it called in-memory cache, why RAM primary storage is faster, and some real world examples of Redis, some different components of Redis, etc. And that pretty much covers all you need to know to be comfortable with caching, to understand caching, to understand the context where it is used, and what are the different components of it, and why do we use it, some real world examples. And next, you can use all these technologies. You can start with Redis, the open source alternative Valkey, right? And you can, depending on your programming language, you can install a library and you can get your hands dirty and see what are the differences in accessing data from a relational database as compared to something like in-memory database like Redis.